Steel has inspired human imagination for centuries. But in the example of buildings, the natural beauty, grace, and sleekness can be even more aesthetically pleasing by exposing the structural steel. The versatility of steel allows the design team to become true artists with the greatest degree of expression. Working together with others in the industry, architects can achieve their most ambitious visions. Structural steel can be bent, rolled, and shaped, welded, and coated to tight design specifications to almost any design imagined, in the safety and convenience of the fabrication shop. Steel can be test-fitted prior to shipping to facilitate rapid construction regardless of the weather conditions. Steel is the most recycled building material on Earth, optimizing sustainable environmental impacts. Structural steel is known for its strength, toughness, and durability. The aesthetic appeal and functionality of structural steel is limited only by your imagination. We've been building with steel for more than 150 years, but it is only somewhat recently that people have started to use that steel in a different way. We call this kind of steel architecturally exposed structural steel, or AESS. This steel is designed to bring both structural integrity and beauty to the buildings. Sharing her views of architecturally exposed structural steel is architect, author, professor at the University of Waterloo, and world-renowned AESS expert, Terry Meyer-Boak.
We've been building with steel for more than 150 years. But it's really only recently that people have started to use that steel in a different way. Steel that has become the architecture of the project. We call that kind of steel architecturally exposed structural steel because it's structural in that it has to hold up the building, and that's always an important part of the process and the means of the use of steel, but it's also become the architecture. And so when we think about architecturally exposed structural steel, we have to frame the design of that steel in a different way that begins to take advantage of the attributes of the steel, but it also requires that we have to think about design with that in a different way. We have to begin to look at the details and the detailing. And so it asks architects, engineers, and fabricators to come up with a new language of expression and detailing when they use architecturally exposed structural steel in order to become very effective with design with this material. AESS, as we call it for short, then becomes the expression of the architecture, and the details that we use with AESS have to be very, very carefully thought out.
The origins of architecturally exposed structural steel have at their roots the British high-tech movement of the 1970s.
When we look at the work of Piano and Rogers in the Pompidou Center that was designed and built in 1977, we see a completely different expression of steel, one that is so extraordinarily changed from the concealed steel that we had earlier on in architectural design. We see a steel that is now very light, that is using custom and standard components in very different ways with very different detailing, to the point where we have custom castings like these 11-ton Gerberettes that become very critical to the expression of the structure and begin to demand a different level of communication in the architectural team in order to bring a project like this to fruition. The use of custom steel combined with standard structural components begins to change the way that we design projects in order to have some economy in the use of standard sections where we can afford that in order to save extra expense for parts of the projects that are more dominant or more visually accessible. When we look at the work of Norman Foster in the Sainsbury Center, we see for the very first time the use of tubes in architectural design. Up until the 1970s, these were simply not available. And so the invention of tubular sections and their adoption in architecture asked architects, engineers, and fabricators to think about different ways to connect these elements, ways that were not even available prior to the invention of these kind of structural sections. We didn't really see architecturally exposed structural steel in North America until the late 1980s, and that would be with the construction of Chicago O'Hare International Airport, which was very important in terms of the history of architectural design, because airports up until this point, which were being designed all over the place to support an ever-growing industry, had been designed most normally out of reinforced concrete. So the selection of AESS for the design of O'Hare was a really important change in terms of putting exposed steel really into the public eye. The thousands and thousands of people that pass through O'Hare every day begin to see steel in a new way. And the detailing of the airport, its expression, the use of the steel, the curves, the types of details that were chosen for this project are very important too, because the airport still holds as a very current expression of steel even to today.
One of the challenges faced with the evolution of AESS in North America since the 1980s until now was overcoming the impression left by some European designers of the need for seemingly unlimited budgets.
For example, the work of Santiago Calatrava, the Spanish architect, whereby the budgets that were assigned to his projects were quite large. And so there was a general difficulty, I would say, with early North American projects in understanding how to adapt some of the more extravagant designs that were normal to his projects and use them in North American contexts where the clients might be slightly more conservative, the budgets were not always excessive. And therefore, we really begin to have to look when we're designing and detailing with AESS, this tuning of the detailing to the project, to the budget, and begin to appreciate that AESS can be designed and detailed quite differently from project to project as a basis of the budget, the use of the building, and other factors that we begin to take into account in terms of fabrication costs. I spend a lot of time at airports traveling to take photographs for my talks and my books, and I was at Baltimore Washington International Airport, and I was out on the curbside and noticed some ironworkers that were busy putting up a steel canopy, and I wondered what it was exactly they were doing. And I realized that they were very busy grinding the welds on some tube-to-tube connections that were going to be up overhead, on top, in a position that nobody would ever see them. And that really got me to thinking in terms of designing with architecturally exposed structural steel, and in particular, the whole notion of grinding welds, which is something that needs to be understood when we're speaking with clients and architects that are worried about the final appearance of the steel, that welds are structural and they're holding the steel together. So if we're deciding to grind the welds off, we are actually removing part of the structural integrity. So that has to be thought out ahead of time. It's also really expensive. And so if we can begin to decide not to do that for structures where people won't really appreciate it, and to save it for places like airports or hospital lobbies or other kinds of dominant structures where people are going to be able to see this detail up close, then that is a better way to proceed when we're designing with AESS. So if we're going to be designing a skylight or a structural system that's far, far overhead that people won't be able to see or appreciate it, then we can soften the details, we can go more for bolted connections or different kind of section types and save the money to be spent elsewhere in the project where it's going to be put to better use. So for example, if we're using AESS on football stadiums, which seems to be a very common method of construction these days, understand that the people going to that stadium are far more concerned as to whether or not their team wins, and it's a good place to go with a more tectonic or rough looking steel in terms of bolted connections. It really begins to suit the nature of the construction, the nature of the use of the project, as well as putting the budget in a more close range with the use of the structure.
AESS can be used across a variety of building categories.
So we have to remember when we're designing with AESS that we're not only using it on high-profile projects like airports, but we are also using it on stadiums, residential applications. And so if we can begin to source our material from standard structural steel sections and use less custom fabrication and welding, then we can begin to make things that are a lot more economical. So one of the things that I like to do when I talk about AESS is to think of it as categories. So we would have the highest category of AESS applied to projects that would, say, use a high gloss finish, like this tree-like structure that's used in a university atrium that has a casting as well at its center. So that would be really, really high-end steel that has very high expectations on all aspects of the steel, versus, say, trusses that are used over an ice rink where we're using standard structural sections just cleaned up to make the geometry and the layout a little bit better than we would expect on a more routine concealed steel project. There are in-between uses of steel whereby, again, we can use standard structural sections, but in this case there's been some rolling done to the sections in order to improve the geometry and the appearance. So it would be partway between sort of a high and a low-end use of architecturally exposed structural steel. We also see steel used in very sculptural ways. So this is a wind mitigation device. So it has a structural requirement to it. But again, what they wanted to do when they were talking to the artist was to really show the nature of the steel fabrication and not cover that up, because it added in a positive way to the texture. So when we're looking at applying AESS, we have all sorts of different factors that we begin to use when we're talking about the way that we're going to detail the project. One of the things that became clear that we had to think about when specifying architecturally exposed structural steel was that it was neither properly covered by the structural steel specification, which was only concerned about the structural requirements of the steel, nor was it covered by the miscellaneous metals specification, which was mostly concerned about the aesthetics of the steel, because AESS has to be both structural and aesthetic.
Specifying AESS correctly has evolved over the years. Specifying too tight can add unnecessary cost to the project. Too loose could affect the visual that you're trying to accomplish. To find that sweet spot and specify just right, keep these major tips in mind.
So the first thing that we really have to think about when specifying AESS for a project is what is the use of the building. There has to be a match between the level of the detailing and the function of the building. So if we select extraordinary detailing with a lot of grinding on the welds for a project that doesn't warrant it, we could effectively price the steel out of the project. So if we have a project like this pedestrian bridge that's in a very high profile location, we can probably afford the kind of exquisite detailing that we see on this project. However, to apply that detailing to another building that is using galvanized steel as a corrosion protection system would be quite inappropriate. So here we can see a project that uses more bolted connections, and so we see a very different approach to the design of these two buildings as a function of their use. So the second aspect that we really have to think about when designing an AESS project is distance to view. If you cannot see the steel up close, then you can begin to soften the detailing, because the distance to view will take that out of your view range and your touch range. So if you think about the design of this airport structure, for instance, the details that are located quite remote from view can be softened. Likewise, if we look at the selection of the members in some projects, we can begin to make more use of standard structural components because these are located at a distance to view, and therefore we do not necessarily need to warrant the expense of a lot of custom construction. The idea of distance to view required members of the community, architects, engineers, and fabricators to understand what value or what distance would be associated with making that decision. Because a specification and a contract and some sort of understanding usually requires a number. And it was decided that the height of a high ceiling, around 20 feet or 6 meters, would be the break point at which we decided something was either near to view or far from view. So you can begin to understand then that overhead structures can begin to take a different approach to the detailing because they would be located beyond this base distance of 6 meters or 20 feet. So if we begin to look at the detailing then of materials and structural systems that are placed close to view, we can begin to understand how the role of the fabrication and the design of the details can be quite different in terms of the way that the projects play out. So you'll begin to see on high-profile projects at a close view range a lot more use of plate material, sharp details, sharp corners, because these can be seen up close to the point where sometimes people can even begin to touch or come into contact with these structures. One of the things about distance when we think about buildings is that distance is something that we view at 360 degrees. We are not always standing below a structural system. There are so many high-profile buildings, particularly ones that use AESS that have atrium spaces, that we need to begin to think about how we view these things, not only from below, but from the side and from above. And so in projects that have atrium spaces that are viewed from all different angles, we have to begin to assess the design and detailing in that view. So if we think about the number of atriums that we experience, we have to look at detailed design that begins to understand the impact of 360 degrees. There are also instances where structures cannot be divided into those that are viewed close up and viewed at a distance. We sometimes have structures that are continuous. So this particular pavilion has a structure that is continually viewed from the bottom to the top, and therefore we have to think about a level of detailing that allows for that continuity in terms of the view and the view distance and the materials. The third aspect that we really need to take into account when we're designing with AESS is the finish on the steel. So that would include whether or not we're using a high gloss paint finish, medium gloss, low gloss, an intumescent coating system, galvanization for our corrosion protection, because all of these systems will reveal the surface imperfections on the steel in a different way. So even though the finish system is something that we're applying at the end of the project, it really needs to be thought about at the very beginning of the project, because it's pointless to waste a lot of time doing grinding of our welds if in fact it's going to be concealed under a very heavy protection system. So for example, an intumescent coating system is slightly thicker and has a finish that's akin to an orange peel, and so therefore it would be appropriate to use that on certain kinds of projects. Whereas if we're using a medium gloss finish, it is a bit more revealing, or if we're using a galvanization process, it's more suited to projects with a more technical connection system than, for example, a project that has continuous welds and a high gloss finish. And so all of this needs to be thought about very carefully at the outset of the project in order to inform the entire design process. One other aspect we need to take into consideration when we're designing with AES is light and lighting. How the steel is lit from below, how it's lit from above, and how that begins to impact our detailing. So for example, when we think about steel in a skylight situation, at night we have steel that is very much illuminated from below, and therefore it enhances all of the fabrication details that we've put into the project. When we see that same steel during the daytime, we see it as a silhouette, and so therefore a lot of those details are masked. But what we have to understand is that we see our steel on a daily basis, at night and during the day, and to take both of those situations into account. There have been major changes in terms of light and lighting with the invention of LED lights, and very often projects are purposefully lit from the interior at night in order to enhance the steel. So we have to understand how the color is going to react with our finishes and our detailing in those instances. Lights can also render colors in different ways. So if we think about changes of light over time, then we can begin to see that when we select a certain color of paint or finish to put on our structure, that might look different based on the kind of color rendering of the light source. So this bridge, which has a red finish on it, looks quite different at night because of the source of the light than it does during the daytime when it is lit with daylight, which tends to render colors a lot more naturally. So the bottom line is that not all architecturally exposed structural steel needs to be equally crafted. That's not to say that it shouldn't be properly crafted, but what we need to do when we think about the use of the building, the distance to view, and the finishing system is to properly match the way that we fabricate and detail the steel to the use of the steel. So there will be buildings that can afford higher levels of detailing, and that is completely appropriate because they have the budgets to afford these. And then there will be buildings whereby we're using more standard structural steel and a different level of detailing. And that's okay too, because it's properly matched to the type of building and the distance to view and the finishing system. So what we're trying to design with AESS is a way to properly match buildings to the detailing system so that we have a very high level of use of AESS throughout the industry.
An important part of the visual drama you wish to achieve can be embellished by your choice of coatings.
Before we go further into detailing AESS systems, we need to look more closely at the impact that our selection of the coating and fire protection system has on the way we proceed. Whether we're looking at an interior or an exterior application, and therefore the weathering on the project, whether or not the project itself can be exposed, if we look at the impact of fire regulations on the design, needs to be considered at the very outset so that we can select appropriate finishes and coating systems to work with our choices in AESS. If we think of the overall finish of the steel, whether it's a high gloss finish, a medium gloss finish, a low gloss finish, a thick or a thin intumescent coating, this must be factored into the overall design of the project in terms of the selection of the member types as well as the detailing of the connections between those members. Steel as a material naturally oxidizes when exposed to air and moisture. One of the things that's important on an AESS project then is to use commercial blast cleaning to completely clean the steel in preparation for all of the processes of fabrication, and as well to ensure that the final coatings will adhere properly. Steel for an AESS project is usually primed prior to sending it to the site in order to protect it from weathering. It's important when selecting the primer to make sure that the primer chemically agrees with the final coating because they do not all work together, and so to ensure a good match, there have to be choices that are discussed amongst the project team. When we're designing with architecturally exposed structural steel, we're trying to match the fabrication detailing of the steel to the aesthetic desires for the final project. So I'm going to show you two steel trees to see how very different the specification might read. The first tree is using steel that is very angular, that uses a combination of welding and bolting in order to achieve its final aesthetic. The second tree uses a combination of tubes and castings, fully ground welds, to create a seamless approach to the design of the steel and the ultimate appearance. So if we look at these two projects and think even of something as simple as a steel tree, we can see very clearly that the specifications wouldn't read anything alike. The invention of intumescent coating systems has allowed much more exposure of steel in architectural projects. It must be understood that the level of fire protection is related to the type of coating and often the number of layers of that protection system, so that will begin to impact the detailing. Intumescent coating systems will often need a top coat in order to make them more useful for areas which have high public contact in order to protect from fingerprints, etc. So it's really good to talk to your consultants in order to determine the nature and level of the system so that you can detail appropriately. Galvanization has become a very popular finish in terms of architectural design with architecturally exposed structural steel. It has to be remembered always that the steel industry looks at galvanization as a corrosion protection system and not a finish. When we are designing with galvanized steel, it also has to be remembered that the elements of steel have to be small enough to fit in the galvanizer's bath. And so therefore, there will be connections required between elements because of this limitation of size. It's important to understand that galvanizing is a very hot process, and that the steel itself has to be a certain thickness in order to avoid distortion in the galvanizing bath. So sometimes for projects with very articulated steel, or for elements that are far too long to fit in the galvanized bath, a zinc protection coating system will be used in conjunction with other elements being galvanized, and these seem to work well together on the projects because the coloration is the same. As an alternate to galvanizing, metallization is now being used as a way to corrosion protect steel, however keep it at lower temperatures. A combination of zinc and aluminum are spray applied to the steel. This allows for the application to much larger members and also is considered a cold process, so we don't need to worry about distortion to the members themselves. The use of weathering steel has become very popular in architecture. When using weathering steel on a project, you're looking at a highly customized set of elements that have to be custom fabricated, usually using a lot of welding with very little bolting that takes place on site. When looking at an AESS project that has a lot of weather exposure, stainless steel is often a good option. Stainless steel requires particular engineering expertise as its strengths are different from carbon steel. It is also going to require that you are using a shop that is dedicated to stainless steel. The equipment may never have been used on carbon steel because any small pieces of carbon fiber that get embedded in the stainless steel will cause rusting on the project. The coating systems that we put on AESS must be designed for durability. So whether we are looking at an interior, exterior, or fire application, they must all be designed to be able to be maintained and to be kept clean and to resist whatever sorts of atmosphere they are exposed to. Cleaning is a big difficulty in many projects because you have to consider the height at which the steel is located, and equipment must be on site whereby routine maintenance is possible. When we're placing steel outside, we have to consider the color, the atmosphere, and the fact that the steel must also be kept clean on a regular basis if it is going to be durable and it's going to continue to look good. Many designers tend to use white as the color for their AESS projects. It needs to be noted that white is not always the most appropriate choice, particularly when we're thinking of building uses that are outside or that may be used as transportation applications, train stations, bus stations, parking garages. Often when we think about these spaces, it might be a better idea to choose a more muted color that is better able to mask the buildup of weather, grime, and can be maintained on a more regular schedule with ease. One of the most fun parts of detailing architecturally exposed structural steel is the design of the connections. The connections, in combination with the nature of the elements that they're connecting, make for the architectural aesthetic of the space. The selection of the members themselves is, however, very important. Whether you're working with standard structural shapes, such as wide flange sections, angles and channels, or plate material, will greatly impact the design of the overall structure as well as the connection details that you're able to use. When we make connections between pieces of steel, we do so for varying reasons. In the first instance, we are connecting pieces in the fabrication shop, normally by welding, because this is easier to do in the fabrication shop, to make the larger pieces that we ship to the site. The limitations in transport will impact our decisions as to what gets done in the shop and what gets done on site. Now, in the case of the pavilion at Brookfield Place in New York City, the diagrid baskets were 5 modules tall, and this would obviously not fit on the truck. Because they wanted an all-welded appearance, they had to figure out how large the pieces could be transported and how to make the connections on site. And so it became a very complex project in order to create these welded connections on site, and this fed into the overall design of the project itself. Breaking the work into site work and shop work was different in the case of Seattle Public Library. Here, the large diagrid sections that were fabricated at the shop were bolted together on the site in order to make for a less complex site erection. The details of these are discreetly hidden and are actually not very obvious to patrons of the library. But you can see that the two projects would be very different in terms of their shop work and their site work because of the decisions that were taken. Bolted connections are commonly used on AESS projects. Fabricators and erectors are very fond of bolted connections because they go together very quickly on the site. Designers have a choice between hex head bolts and tension control bolts when making their decisions. The aesthetics of both are quite different and can change the overall appearance of the project. It is very simple in an AESS project to ask of the fabricator and erector to have a consistency of the bolt head on one side of a connection or the other, and this creates a much higher level of appearance for the connection, even of the most basic technical connections. Most commonly, to connect a tube to another tube, a plate would be welded to the bottom of the tube and bolts would be applied around between these connected plates. There are many other ways as well to create these kind of connections whereby plates can be set into the tubes, lap joints can be created, so you can see through the various connection details illustrated that there are quite a few different aesthetic takes on the bolted connection that can be applied to tube connections on varying architectural projects. The designers of the Rose Center for Space were using a tubular structure with connections within the trusses that were made using bolting. To create a very simple yet effective connection detail, they tapered the plates that were attached to the ends of the tubes in order to work with the geometry and to create an aesthetically appealing bolted connection.
The fabricator typically does a fit test to assure all pieces go together in the field. Not all structures can be delivered in one large piece. Dependent on the street widths and overhangs, your design may also need to consider transportation.
Transportation limitations will infer that we do splices between larger members of the structure on the site. This does not always have to be done with welded connections. We can use discrete bolted connections. If we look at some of these details, we can see how effectively we can eliminate welding and use bolting by keeping the lines of the overall design of the structure in mind when creating either lapped connections or other kinds of discretely designed connections. Architects seem to have had a lot of fun detailing these, but please bear in mind if these are located outside, care must be taken to ensure that water does not pool in the connection and therefore corrosion is prevented. The extremely long triangular trusses that were installed at this airport were obviously too long to be shipped in one piece. They were shipped in three, and therefore they used a combination of bolted connections and discrete connections to make the site connections. If you look at the type of hidden connection that was used on the bottom chord of the truss, you can see quite rudimentary bolted connections have been used within the confines of the round HSS tube, and cover plates applied over top that once painted disappear from view in the final product. If a completely remediated welded connection is desired, this is how it's made. They will create a pair of tubes, male and female connections, with tabs on the side for temporary bolting. Once the welding is completed on site, the tabs are removed, any defects are ground away, the weld itself is ground away, and any imperfections filled with body filler. This is sanded, then primed, and the final paint coating is applied. So if this is done with a highly skilled crew, you should not be able to see where that welded connection has taken place. But you can obviously understand how much more expensive this would be to fabricate than any kind of discrete connection. When selecting welded connections on an AESS project, a complete different set of considerations must be taken into account, because normally we are selecting these because we want a seamless appearance. If we look at this structure that's using square HSS tubes, the designer wanted these tubes to be in plane with one another when they crossed. So therefore, the connection from tube to tube required a lot of remediation in order to make that welded connection disappear. So we have to think about these detailing choices and understand that this is going to impact the fabrication time and the cost on the project. This project, for instance, is a conical structure that is using round HSS tubes. They've been able to detail the connections more economically because there is consistent geometry in the project, and they've managed to do this with straight cuts and unremediated welds. The previous project created a conical structure using straight tubes, which made the connection from tube to tube quite simple. In this project, to create a tubular bridge, elliptical shapes needed to be made from the tubes themselves. As they cross over, one tube is allowed to go straight through for structural continuity, and the other one is cut to fit. So this ends up requiring significantly more detail in terms of the way that the cuts are made, but also you can see here that they have left the welds as is because it was decided that it was too expensive to remediate the welds and that the distance to view, the location, and the use of the structure didn't warrant any remediation. This pedestrian bridge also uses tube-to-tube connections. The way these are made is very typical for many projects. The cuts are first marked on the tubes. Tubes are cut and welded together in place using tack welds. This allows for fairly quick fabrication and the time for the ironworkers to create multiple pass welding to make the connections fully structural. In the case of this particular bridge, remediation of the welds was not done because of its position and its use. The project was metallized for corrosion protection, again due to the size and the shape of the structure. It was given a prime coat and a finish coat and put in place. This fabrication would be typical on many projects using tubular materials. There are some connections that have evolved from the high-tech movement to now that simply demand certain fabrication practices that require ground welding in order to make them look good. The tapered end of a strut is one of those connections, and these are often used to connect larger truss members to vertical posts or to create bracing systems within buildings. The way this is fabricated is by taking the tube and cutting out an elliptical section from either side, cutting an elliptical plate to fit in this to create the taper, welding, grinding, and putting attaching plates at the end. Although the fabrication method and design is similar from project to project, you can see different instances where the actual design varies from project to project, creating a somewhat unique detail, although with a very similar fabrication method throughout. We've seen that there's a significant amount of design detail in AESS that can be achieved using standard bolted connections, welded connections, combined use of standard structural shapes, hollow structural shapes, that doesn't require much in the way of custom fabrication. Custom fabrication is typically done using plate material and therefore adds significant expense to the budget for the project. So we see that we need to apply custom fabrication to projects that warrant it by examining the use of the building, the distance to view, the level of finish, as well as the budget impact. We've already looked at the work of Santiago Calatrava as being very influential in the design of AESS structures, but we have to realize that most of the work that was done by this architect for these large-scale projects was custom fabrication and therefore might not apply to all projects.
Custom fabrication, combining steel plate and standard structural shapes to design unique and economical forms.
We're going to look through a series of projects that use custom fabrication as an essential part of the design aesthetic for the space. Normally, the custom fabricated structural parts use plate material to create forms that could not otherwise be fabricated from standard materials. In the first, trapezoidal forms were desired for the columns and the spanning members. So these were made from cut plate material. But even here you can see affordability and economy in detailing was a priority. The connection between the intersecting plates was made in such a way that one plate was set back from the other. This allowed for a simple fillet weld to join the plates, as well as creating a nice shadow line on the structure itself, thereby creating a more interesting detail. To have had the plates be square to each other would have required significant weld remediation, increased the cost of the project significantly, as well as removed the interesting detail that was afforded by setting one plate back from the other. So what we begin to see driving the use of custom plate steel is the need to make sections that are longer than can be accommodated in standard structural shapes, as well as the creation of crisp corners to create the box sections. So it becomes all about the design of the corner when creating these details. Although on first look, the elements that were used for the observation level of the shard may appear to be wide flange sections, we can see by the sharpness of the corners that plate steel was actually used. Interesting geometries for some of the plate steel to take advantage of the use of fillet welds. Various custom details were used in the fabrication and design of the New York Times building by Renzo Piano, from the design of the vertical columns to the horizontal spanning members to the connection details that form the end points of the cross braces. Custom plate steel was also required in the Leadenhall building for the fabrication of the extremely long members of the diagrid megaframe. Custom plate steel was also required in the design and fabrication of the nodes that had to take 6 to 12 incoming diagonal members. The use of custom plate steel was required on this project in order to put added steel where it was required in order to properly transfer the loads through the structure. The precision afforded by custom-cut plate steel works well when considering the use of expansive cable-supported glazing systems. Here on the Newseum in Washington, D.C., we use a cable-supported glazing system in conjunction with very large vertical trusses which have been cut from custom plate steel. On AESS projects, it is always possible to combine custom steel with the use of standard structural shapes. We should always use what is appropriate to the particular application. So here on Cannon Street Station, we have certain elements of the very large specialized truss that have been fabricated using custom plate steel, and yet other elements which are using standard structural shapes and tubes because these are more appropriate to the system. The curved box sections that were fabricated for the Arganzuela Bridge in Madrid, Spain, wanted to have crisp corners. However, the filtered light that comes through the screens on the bridge allows for the use of unremediated welds, as these fit in well with the overall texture of the bridge.
Another advantage of steel is the ability to maintain great strength, whether in compression or tension. Let's take a look at some opportunities available using tension systems.
One of the greatest advantages of steel is its ability to work in tension. We can use members of very small diameters to achieve great strength if only tension forces are applied. One of the key design elements in many AESS structures will be the use of tension cross-bracing to stabilize the structure. Many new details had to be developed in order to create a design language for the use of cross-bracing in AESS projects. The design of the center plate of the cross-brace has become a feature on many projects. Here for the cross-bracing design of the trusses at the Burj Al Arab, they have done a lot to minimize the appearance of this centerpiece. Tension members, in the form of rods or cables, are often used in suspension systems for bridges. Here we see pictured a pedestrian bridge in London, England. The design of the plate fan at the top has been very carefully done in order to distribute the location of the clevises in a clever way to support the bridge. The design of the tie-down for suspension systems is also quite important. Here we see again clevis attachments used in order to attach this to the base of the bridge. Perhaps one of the best designed attachment systems that I have come across for the connection between the mast and the cable is pictured in that of the Sony Center in Berlin, Germany. Geometry plays a very important part in this design. With a good understanding of structure and the use of tension versus compression, many AESS projects have had fun with force differentiation as part of their design. Here you can see in the design of the Grand Arch at La Défense the use of force differentiated structures to push and pull the canopy and put it in its form. Again, we're using tie downs to the base and tie backs to the main structure in order to hold everything in place. We can see a very inventive use of force differentiated structures in the design of the arches at Porto International Airport. Here, large round tubes, thin cables, and struts are used to create visual interest in this space. Steel tension systems are critical to the design of the Phoenix Public Library. Here they are used on the exterior shading system to give the fabric form, as well as on the interior to create an actual separation between the top of the columns and the support of the roof structure above.
Dramatic visual impressions can be made by using curved steel.
The use of curved steel in AESS can create innovation in the projects. There are various ways to create curvature in AESS projects. The first and most obvious is to actually bend the steel. This can be done with a bending machine, which is a 3-point pressure system, with a brake press, or with a plate rolling machine. We can also facet the building in order to give the appearance of a curve without actually curving any of the pieces. Lastly, we can cut curved pieces out of plate material to support the forms. There are various technical issues that designers must appreciate when specifying bent steel. The size, the dimensions, and the length of the steel itself must be discussed with the bender roller to make sure that the plant can accommodate it. If steel is curved too much, it can deform, and this is bad for the look of the project. The bender roller will refer to the orientation of the steel in the bending machine as hard way or easy way. Some shapes are more difficult to bend in certain orientations, and so this also has to be discussed with the project in terms of the orientation of the members. Steel bending is very equipment dependent. When bending extremely large tubular shapes, we will normally have to use induction bending, as this can accommodate these large diameters. Smaller diameters are well accommodated by a 3-point pressure system. Here we have to be sure that the bender roller has the appropriate dies to accommodate the specific shape of the section that you desire to bend. Bending steel is still very craft-oriented. It is up to the skill of the operator to determine when the actual proper curvature has been reached. It has to be understood that because of the geometry of the bending process, there will always be a residual straight end at the end of the piece of bent steel. This can easily be cut off and recycled and put back into the steel processes. It has to be understood that the steel comes into the roller bender's shop straight and leaves curved. So as a function of the curvature, it may or may not fit easily on a truck. This may require cutting the long pieces of steel into segments that have to be rejoined at the fabricator's shop. The precision of the curve is checked on an ongoing basis using a plywood template. Probably one of the most famous applications of curved steel is in the overhead canopy at Millennium Park in Chicago. Here we can see splices that have had to take place over the field in order to accommodate the extremely long lengths required. Splicing bent tubes is not straightforward. If the curvature is extreme, deformation of the tube will usually occur. It will take great care in the fabrication of the splice to ensure that the weld is properly backstopped. Even though the bent steel on this spiral staircase was not left exposed, it does show us the intricate requirements of fabrication as a result of the combination of curvature, tubes, and splices. In high-profile applications of curved AESS that requires a splice, high-quality fabrication is absolutely required in order to make the the welded connections fully remediated. The extremely long curved tubes that were used for the diagrid baskets at the World Financial Center entry pavilion required that they be divided into many lengths for transportation to the site. So these, in order to create a continuous look, had to have fully remediated welds that were done on site with great care to achieve an excellent final product. Extremely large tubes can also be bent using this specialized equipment. When sizing extremely large tubes for projects, it is important to check with the roller bender to see how large tubes can be accommodated. This is the type of equipment that would have been used for the large tubes on the Canadian Museum for Human Rights and the Amgen Helix Bridge in Seattle, Washington. Plate steel is rolled with specialized equipment which also uses a 3-point pressure system. This is the type of equipment that would have been used to roll the plate steel for the box sections on the Arganzuela and Puente de Luz bridges. Break forming is used to create plate steel with inconsistent curvatures. Break forming is a very craft-based process. The operators must very carefully mark the steel to determine the spacing of the hits of the brake press in order to have the end result curvature. The curvature of the beautiful treads of this stair at the Boston Society of Architects was done using break forming. Completely remediated welds were required to join the U-shaped treads to the plate steel at the sides to continue the illusion of continuity that you see in this piece. Oversized steel tubes are made using break forming. Here you can see the pressure of the brake press revealed on the interior of the tube, but the pressure is controlled so this does not translate to the exterior of the tube. Tapers and cones are always custom fabricated using break forming. So anytime we see these on an AESS project, we need to understand the requirement for break forming to create these elements. The beautiful colored legs at the Ontario College of Art and Design have fully remediated welds to connect the tapered cones at the bottom to the diameters at the top for continuity of the form. A donut-shaped steel plate is used on the interior in order to backstop the weld and reinforce the connection. The long conical supports at Barajas Airport had to be fabricated in several lengths due to the limitation of the size of the brake press. The connecting welds were left unremediated, saving greatly on the cost of the project, and this was quite appropriate due to the size of the structure and the distance to view. A newly popular method of connecting steel is the use of very large castings. Some of these castings come in the range of 31,000 pounds. It's said that when you're making a connection between many members with varying geometries, that if the cost of fabrication exceeds 4 times the cost of the steel, then it's time to consider using a casting. So what a casting can do then is to simplify the connection. What's really interesting to me about castings and the change in castings from the 1800s, where they used cast steel in order to create ornament and detail and make things look quite intricate. Nowadays we use castings for the exact opposite reason. We're trying to simplify the connection. So for example, the Queen Richmond Centre in Toronto has a 31,500 pound cast node that's joining the 8 legs of the delta frame. So each of these tubular legs is maximum around 39 inches in diameter, and they're all joined through this hollow cast node. This entire system is filled with cast concrete in order to give added stability as it is holding up 11 stories of building above. Another project that has used a casting as its central piece is the science building at the University of Guelph. The exterior branches are also using castings to connect one piece to the other. When fabricating very large cast nodes, the form is made using resin and sand, and therefore the surface of the casting is rough and somewhat resembles an orange peel. So when using these in projects, decisions have to be taken to either remediate the surface, that is, to grind it to make it appear more like the adjacent steel, or sometimes to put a reveal or a detail where the added pieces join the steel in order to make a feature out of the different textures in the project. There are two distinct kinds of castings that are used in an architectural project. One would be the unusual castings that would form a centerpiece, and these are all made one of. So therefore, in order to create the casting, the mold has to be destroyed to get the casting out of the mold. So it is less of a problem to create these differently one from the other, and they are normally used on highly customized projects. The other kinds of castings that we see would be the castings that we are using as clevis attachments, and these would be used in conjunction with tension systems. Probably the most significant project in the United States at present that is using castings quite extensively is the Trans-Bay Center in San Francisco. In the Trans-Bay Center, because of the sheer size of the project, many of the castings are identical, giving some economy through repetition.
AISC does the Ideas Awards for steel buildings, and I've noticed many of the award winners are architecturally exposed structural steel. Do you see this trend as kind of the hip, sexy trend in construction these days?
I would say yes. When I first started to research AESS in the mid-2000s, say around 2004, 2005, when I started to really look for buildings to take photographs of to use in my research and my teaching and my books, I was hard-pressed to find a lot of really good examples. And one of the things that I've noticed today, 10 years later, is that I keep tripping across amazing examples everywhere. So I would say it's really taken off. A lot of the product is fantastic. And I think it's creating not only sexy, but really inspirational places for the public. Whether they're aware of the steel or not, I think that kind of quality of space, of structure, really begins to have a positive impact on people. I know when I go to airports, when I'm traveling, the ones that I find the most comfortable to be in are ones that are using exposed steel. Some of the older airports that are kind of dingy make you feel bad when you travel, whereas if you come into some of the newer, entry halls that have, large spaces and structures, I think it really helps to improve, people's lives. And so, yeah, I would definitely say it's the sexy steel, and it's really taking off in a big way.
Structural steel is the most widely used building material. While the use of architecturally exposed structural steel is relatively recent, it appears it will be with us for the rest of our times, and for good reason. Your designs may be limited only by your own imagination. For design guides and more information on AESS or structural steel in general, please visit aisc.org.